Hello everyone, welcome to lab number 5. All right, quick little recap. Lab number 3, we introduced the concept of force, how to measure it, that it was a vector quantity, and we saw in lab 3 that there is a proportional relationship between the force and acceleration. Now, what a proportional relationship means is that if we take the two variables, force and acceleration, and we divide them by each other, any pair of the two will have the same ratio. That is to say, for example, if we have 2 newtons of force, that gives us 1 meter per second of acceleration. The ratio is 2. That means if we go to 4 newtons of force, we should expect to see 2 meters per second. If we see 8 newtons of force, then we would expect to see 4 meters per second squared. It does not mean, a proportional relationship does not mean that the force, that they increase. Parabolas increase, cubics increase, exponentials increase. It means that there is a specific ratio, and it's of the form y equals kx, where y is the independent variable, the dependent variable, x is the independent variable. Also, the difference between the two, the independent variable is the variable that the experimenter chooses and changes. The dependent variable is the output of the experiment. So think of it as a box. That box is the experiment. The independent variable goes into the box. The dependent variable comes out of the box. Okay, so that gives us that little explanation there real quick. Let's go on and continue this little recap. We saw that there was a proportional relationship between force and acceleration. It looked like that maybe mass was involved, and that leads us into an observation of Newton's second law. Whether or not that's the case, we'll find out today. In lab number 4, we saw that if we took multiple forces and put them together, it affected the acceleration. If we had 2 forces pushing and pulling in the same direction, we increased the acceleration. If the forces opposed each other, the acceleration decreased or even disappeared, depending upon what direction the forces are. Which leads us to another modification. We first start off with forces are proportional. That little thing means proportional to acceleration. Now what we can say is the net force, or the sum of the forces, is proportional to the acceleration. Okay, big difference here. Force does not equal mass times acceleration. I can apply a force to an object and it would not accelerate. The reason why it wouldn't accelerate is because there's an opposing force that's stopping it from accelerating. What causes acceleration is net force, the sum of all the forces together. And that's what lab number 4 expounded on. Now the question is, what really is the constant of proportionality? What is it that we multiply acceleration by that would give us the number of the net force? And so that's what we're going to do here in lab number 5. In investigation 1, we're going to take a look at force, mass, and acceleration. And here's what we'll see if we can find the relationship. What happens if we keep the force constant, but we change the mass? Okay? We've got 3 variables already. We've got force, mass, and acceleration. In lab number 3, we changed the force, kept the mass constant, changed the acceleration. In lab number 4, we added forces onto it, which had the same effect. Now here in lab number 5, we're going to keep the force constant, but this time change the mass and see how it affects the acceleration. Okay, so let's take a look on page 111. I've got it set up here. What we need to do, step number 1, is we've got to take our cart with our force sensor on it. And what we need to know is we got to define a mass scale. Now the mass scale we're going to define is going to be multiples of cart masses. And that's the reason why I have cart mass written up here. Okay? So how much is a cart mass? Well, I've already measured, and it turns out that 1 cart mass is 850 grams, or 0.850 kilograms. I've already measured this, and so now we can do all of our additional or subtractions to the carts using those numbers. I'm sorry, I made a mistake here. It's not 850 grams. It's 350 grams, or 0.350 kilograms. Okay, so there's the correction. 0.350 kilograms. 250 grams for the cart, 100 grams for the force sensor. Okay, so first thing we're going to do is we're going to add enough mass to make the cart 2 cart masses. That means I've got to add another 350 grams. This black brick here, this is 250 grams, and from my hanging masses, I'm going to add a 100 gram hanging mass. So I'm going to put those in the cart, so now the total mass of the cart is now double. 2 cart masses, 700 grams. Okay, so we record that step number 5. It's going to be 0.0700 kilograms. Okay, we've already got the computer set up for applied force, acceleration, and velocity. So let's go ahead and do the experiment. So I'm going to pull back here. I'm going to zero the force sensor so that it has no weight on it. Pull this back all the way. And I need to get this out of the way so it doesn't get in the way of the cable. Okay. And again, I've got triggers built on it so that the only thing that's recorded is the cart as it's accelerating. So let's go ahead and do the experiment. Okay, and there's the data right there. Okay, so the question now is, activity 1-2, let's go ahead and record the information on the graph on page 112. First of all, where it says 2 cart masses, what's the average applied force? I'll go ahead and use the statistics function on applied force and come up with 0.031 newtons. Okay, so my force for 2 cart masses is 0.31 newtons. Next, I need to find the average acceleration. There are 2 ways of doing that. I can either use the average of the accelerations, and the average of the accelerations in this case is 0.31 meters per second squared, or I can use the slope of the velocity versus time graph, and I'll use the best fit line there, and I come up with a slope of 0.31 meters per second squared. So let's go ahead and use that 0.31 meters per second squared, 0.31 newtons of force for 2 cart masses. Activity 1-2, accelerating the cart with a different mass. Prediction 1-1, suppose you remove mass from the cart until it's only 1 cart mass and accelerate it with the same applied force. Compare the acceleration to that of the larger mass cart. So, what is going to happen if I take mass off of this cart? Is it going to have a bigger acceleration, a smaller acceleration, or is the acceleration going to be the same? The only thing I'm changing is taking mass off the cart, so we're looking at just the mass of the cart being accelerated by the same weight. Let's go ahead and do that. Comment. You'll want to accelerate the cart with the same applied force. As you may have noticed, the force applied to the force probe by the string decreases slightly once the cart is released. You'll explore why this is so in a later lab. This decrease depends on the size of the acceleration. Therefore, in order to keep the applied force constant, you may need to change the hanging mass slightly. So let's go ahead and zero the force sensor. I'll pull this back here. All right, let's go ahead and repeat the experiment. Okay, if I take out that piece of force at the very end, where the cart bounced against the bumper, let's go ahead and get rid of that data there. Okay, so what are our averages? Well, we see that the force, I'm going to go ahead and keep it this way. Okay? What we see is the applied force is 0.30 So for one cart mass, here we go, there's my black pen, excuse me. So for 1.0 cart masses, we have an applied force of 0.30 newtons, so that's close enough for our purposes. It's less than 2% difference. And the acceleration, by looking at the slope, we see 0.54. If we look on the average of the accelerations, we get 0.56. Let's go ahead and call it 0.54. So the acceleration is 0.54 meters per second squared. Question 1-1. Did the acceleration agree with your prediction? Let's see. I doubled the mass. I won't necessarily say that I doubled the acceleration, although it looks pretty close. 0.54, 0.31. Let's go ahead and repeat the experiment. Let's see if I can get a little bit more force out of it. I need to add 1/100th of a newton, so that means I need to add, let's see. If 30 grams gives me that, so I'm going to add 2 grams and see if that makes a change. By the way, a little aside, I'm using 30 grams of mass. So we'll zero the force sensor, and we'll repeat the experiment and see what we get as far as the acceleration. This is still activity 1-2. Okay, the force turned out to be 0.32. The acceleration turned out to be that did make an effect. Okay, it did make an effect. When I added the 2 grams, it did affect things. So I'm going to do one more, but this time instead of adding 2 grams, I'm going to add only 1 gram. And again, we'll repeat the experiment. And I'll also do one more correction here. I'm going to change the recording condition so that the stop trigger, we don't get the bounce taken into account. Okay, so that changes the stop trigger. So let's go ahead again. We're going to repeat activity 1-2. I've added some weight so we can get the same force measured on the force sensor. So let's pull it back. And now let's see what happens. Excellent. That is perfect. That's exactly what we want to see. We see that the average force was 0.31. So let's go ahead and make that correction. The average force turned out to be 0.31. And if I take a look, my acceleration was 0.62 on the slope, 0.64 on the mean. So let's go ahead and use the slope, and I get 0.62. And you really can't ask for much better than that. If you predicted that if we have the mass, we're going to double the acceleration, then you were spot on. That's a very interesting relationship there. Question number 3. Now let's make the mass of the cart 1.5 cart masses. So 1.5 cart masses. Half of 350 is 175 grams. So let's go ahead and add 175 grams. 50, 20, and 5. That's 175 grams that I've added on. We're going to zero the force sensor. The first run we're going to do is just to see what the force is. The force was 0.31 newtons, so therefore I'm going to keep that data. And so for 1.5 cart masses, 1.5 cart masses, we end up getting a force of 0.31 newtons, and we get a mean acceleration of 0.46 on the average of the accelerations, 0.45 meters per second squared on the velocity. So let's use the velocity slope, 0.45. That 0.3, 0.45, we're starting to see something here. It looks like there's something numeric going on here. So let's repeat the experiment. with 2.5 cart masses. 2.5 cart masses means I take 175, I take first 350. I double that. Shoot, let's do it on a board just to keep track of it. So 350 doubled gives us 750 grams. To that I need to add half of 350. Half of 350 is 175. Let's add that together. That's 5, 2, and 9. So I need to add 925. I have to have 925 grams total. Okay? 925 grams total. If I subtract out the mass of the cart, 350 is, let's see, that becomes 575 grams. So if I take 350 grams for the cart plus 575 grams for the added mass, that will give me the 925 grams for 2.5 cart masses. And now 975, that's right. So we now have 350 plus, I'm sorry, I'm going to have to do this all over again because I lose track of it. So I have 350 grams. 350 times 2.5 gives us 700 plus 175, which happens to be 875 grams. Ah, there we go, 875 grams. Okay, so 350 plus 875, or minus 350, is 525 grams. There we go. That's not right. 8 minus 3. Oh, yes, that is 525 grams. Sorry, sometimes my math gives me trouble as well. So all I got to do is add 525 grams. This is a 250 gram brick. So I take 2 of the 250 gram bricks, and then I add 25 grams of the hanging mass onto it. And that gives me the amount of mass I need. I'm going to take off the 1 gram mass, and we may have to take off some more mass later as we go along. So let's go ahead and do the experiment now. Pull this back. All right. We're going to 0 the sensor so we get an accurate reading. Start recording. Okay, the force is perfect. The force is 0.31. So we get 0.31 newtons of force. What do we get for the acceleration? For the acceleration, we get 0.28 on the average of the accelerations, 0.28 on the slope of the velocity graph. So 0.28 is our acceleration. Well, now we're starting to see something. We may have to repeat this experiment. There's something a little off about that, but we'll look at that again. Let's go to 3 cart masses. 3 cart masses then would be 350 grams for the cart, plus another 700 grams, and I think I see where I made my mistake. No, I didn't. So I need to add 700 grams, so there's 500 grams there. Then we add 2 100 gram masses, and that gives us our 700 grams. Let's repeat the experiment again. This is the run with 3 cart masses. 0 the force sensor. Let's do 0 the force sensor one more time. And now let's see what happens. Okay, the force is a little bit on the high side, 0.32. So what I'm going to do is I'm going to take some mass off of the mass holder at the end. Okay, so I'm going to go ahead and take off a gram just to make sure that we have the same mass, or not the same mass, but the same force. So we'll zero the force sensor. Actually, we'll pull this back. This is part of the adventure, isn't it? You see, what we're trying to do is we are trying to keep the force constant and just change the mass. All right. I made an obvious error there. Notice where the force is. The force is now reading 0. What that means is I zeroed the force sensor while there was weight hanging on it. So I'm going to go ahead and delete that run, reset it. This time, make sure that there is slack when I zero the force sensor. And now we'll repeat the run and see what happens. Okay, I'll go ahead and keep this average force. This average force turned out to be 0.32, but you saw for the most of the run it was 0.31. The mean was 0.22 for the average of the accelerations, and we have an average acceleration of 0.23. So let's go ahead and use that. So 0.31 with a 0.23 average acceleration. Okay, so that goes through extension 1-3. Now the question becomes, what's the relationship between acceleration and mass? So we're going to go ahead and plot the graph of the average acceleration versus the cart mass. I have it already set up on page 2. There's my graph there, and I'm going to plot on the graph, let's see, we want to put average acceleration on the y-axis. So mean acceleration goes on the y-axis. On the x-axis, we want to put cart masses. So there's mass in carts. So let's go ahead and do that. Cart mass of 1. We had an average force of 0.31. We had a mean acceleration of 0.62. And there's the data point there. Next, we're going to have 1.5 cart masses. That had a force of 0.31 and an acceleration of 0.45. And there's a line there. Let's go ahead and rescale, and we'll rescale it one more time when we do the next one. 2 cart masses with an average force of 0.31 and a mean acceleration of 0.31. And now it's starting to rescale automatically. Good. Next, we have 2.5 cart masses with a force of 0.31 and a mean acceleration of 0.28. And we're going to finish off with 3 cart masses with an average acceleration of 0.3, with an average force of 0.31 and an average acceleration of 0.23. And there's our graph. And we have an issue here. Okay. I really don't have a problem with the first 3 data points. The last 2 data points seem a little bit off. So what we're going to do is we're going to go ahead and repeat the experiment for the last 2 runs and see if we can get the same data points. Okay? Because when I zoom out, let me go ahead and zoom out on the mean acceleration and zoom out on there. I really cannot see a relationship. It looks like it could be linear. Maybe not. Don't know. So the nice thing about this is we'll just go ahead and repeat the experiments. Okay, I've just reset and I've done some recalculations. And so here we go with the 2.5 cart masses. And let me go ahead and repeat the experiment. Start recording. Let it go. Average acceleration of, the average force is 0.31 is what we expect. We see the mean acceleration is 0.27 And we see the slope is 0.27. So let's change this 0.28 to 0.27 and see where we go with there. Makes a little bit more sense. 0.31, that's 0.27 is kind of halfway in between. Now let's do the last one, which is the 3.0. And for the 3.0, I need to add 700 grams of mass. So there's 700 grams of mass added on. 0 the force sensor, and let's give it a run. 0.31 with an average acceleration of 0.23. So let's go ahead and keep that. That means we need to take a look at our graph on page 2. Change this from 0.28 to 0.27. That looks a little better. I mean, it doesn't. I'll tell you why. It looks a little better because it seems to make a little bit more sense that it falls in closer that way. So anyway, let's go to activity 1-4, the relationship. Does the acceleration of the cart, on question 1-2 on page 113, does the acceleration of the cart increase, decrease, or remain the same as the mass of the cart is increased? And as we see, as we increase the mass of the cart, the acceleration is going down. That gives us the discussion on the top of page 114. There, you see on the right-hand or the left-hand side, we have a linear relationship, but it is a negative slope. On the right-hand side, though, we see a curve that looks more like what we see on our graph here. And this is called an inverse relationship. And an inverse relationship is of the equation y equals b plus c to the x. Or, here's another way of putting it. Okay, our inverse relationship, and you can't see this. But let's just look at this. The inverse relationship is of the form y is equal to x divided by a constant k. So we get something very interesting there, and we'll talk more about that later on. Let's take a look at the fit routine and see if that's actually the case. So I'll use, there's linear. Let's go down to inverse with no offset. We click on that, and we see it's a very, very close fit. It has to be an inverse because if it's linear, that means there's got to be some point where if the mass is big enough, the acceleration would be negative, and that makes no physical sense. So an inverse relationship seems to be a close fit. A more direct inverse relationship is a little bit better of a fit, not that much difference. So we can definitely say that there is an inverse relationship between the force and the mass. Or rather, there's an inverse relationship with a constant force between the mass and the acceleration. Question 1-4. In the previous lab, you found that the acceleration of the cart was proportional to the combined applied force when the mass of the cart was not changed. State in words the general relationship of the applied force, the mass, and the acceleration that we have found. If the combined net force is sigma F, and the mass is m, and the acceleration is a, write a mathematical relationship that relates these three physical quantities. So in words, we have net force is proportional to acceleration. We have acceleration is inversely proportional to mass. So to get that, we would have to write the equation which says that net force sigma F equals m times a. And from that equation, we see the relationships. And we'll talk more about that when I get into investigation 2. Thank you very much. Again, if you have any questions, please contact me.